Hi, I'm Peter Marshall. I work on V8 at Google. This is my first conference talk, so go easy on me. Who is from a really different time zone? OK, cool. Who is really jet lagged? OK, who had a nap today? Yeah, seems about right. OK, so as I mentioned, I'm Peter, and I work on V8 at Google. I've been working there about 13 months from the Munich office now. I moved there from Australia, where I went to Australian National University. And yeah, I pretty much moved to Munich to work on V8. I'm mostly working on Node.js performance features in V8, so looking at what the Node.js use case is for V8 and just trying to make that as fast as possible. So the question I want to eventually get around to answering is, what does fast, modern JavaScript look like on the web today? But first, we should just briefly cover what exactly V8 is. I think most people saw Franzi's talk this morning, so we'll just recap in a small amount of detail. But V8's the JavaScript engine inside of Chrome and Node.js, so anytime you're running JavaScript, we are running it in V8. That's pretty much it. So the talk's going to be structured around, I'm going to talk about this idea of language dialects. And this is really interesting. It's been coming up a little bit online, and people are starting to talk about it. But I mean language dialects in terms of dialects of JavaScript. Then I'm going to talk a little bit about the architecture of V8. And then I'm going to get around to some code examples and some benchmarks. So why do we care about speed of Node.js and speed of JavaScript in general? Well, obviously, servers cost money. If you're serving to hundreds of millions of people and you can cut a few % here or there, then that's really good. That's going to save you a lot of money. We know that users click away from sites that aren't responsive or don't provide that content fast enough for them. But on top of that, we're not just talking about 1 or 2% performance gains here or there. So we're talking about transformative use cases of the language, so things like Node.js, for example. So 15, 20 years ago, people weren't running JavaScript on the server, and it certainly wasn't as widely used as it is today. So we're not just talking about 1 or 2% gains. We're talking about changes in the way the language is used. So people ask me, why isn't JavaScript performance already a solved problem? And this is basically like saying, why do we need you? Like, why do you have a job? It's kind of rude. So there's a few reasons here. So why I still have a job? The language is growing. So we're adding new things to the language through to the TC39 process, and we're adding things to the ECMAScript spec. So we have to implement new things. OK, this is actually not as much of the work we do as you would expect. It's maybe like 15, 20% is like just adding the new things. OK, the language is really high level. And we're talking about JavaScript, which we all know and love. And we're talking about this low-level language of assembly that CPUs understand. And V8's job is to take this high-level language and turn it into this low-level language. And there's always some trade-off in there, and you always have to make some decision about what is optimal there. And there's no sort of perfect way to do that. So that's really difficult. Third thing is that performance on low-end mobile is definitely not solved. So if we're talking about a $50 smartphone, then you're still looking at like 20, 30 seconds to load a web page. So this is a really different use case to a server, which has heaps of RAM and heaps of solid-state drives and stuff like that. OK, but probably the biggest thing is that people change the way that they're using JavaScript. And yeah, this is a theme that's going to come up. So people change the way they use JavaScript. So there's plenty of ways to do something in JavaScript, right? So you can do a for in, a for of. You can do a for with your I++ and iterate through it. You can do a while loop. You could just write 100 if statements in a row, whatever, right? And most languages have this sort of flexibility. But what is about JavaScript that means that we change the way we use JavaScript so much? Well, it turns out that when you are constantly changing the way you use JavaScript, or when you have a lot of choice, this sort of leads to common idioms and styles that form dialects of the language, much like actual languages, right? OK, so I want to talk about this thing called CrankshaftScript. And this is sort of like, yeah, this is due to a bunch of performance advice that maybe we were talking about 2 or 3 years ago with JavaScript and V8. So what is CrankshaftScript? OK, so CrankshaftScript is a language, is a JavaScript dialect. And the purpose of it is to run as fast as possible in V8's Crankshaft compiler, right? OK, cool. So if we go back to that original question, which was how do I make JavaScript run as fast as possible, and I've just told you CrankshaftScript is super fast, then you're thinking, yes, OK, talk's over. We got it right. It's CrankshaftScript. OK, so sorry to disappoint you, but we actually removed Crankshaft recently. I love this CL, like +2. Why? So Crankshaft is gone now, so OK, you can't just write CrankshaftScript. It's not going to work. OK, so what was Crankshaft? Crankshaft was the optimizing compiler inside of V8. OK, what's an optimizing compiler? Just briefly cover the architecture here. OK, there are boxes missing from this diagram, right? But this should give you enough of an idea. So we have JavaScript code coming in, and we have this baseline compiler called full code gen. This is what V8 looked like a few years ago, right? It doesn't look like this anymore. So we have full code gen, which is a baseline compiler. And full code gen's job is just to run the code as fast as possible. So it spits out some baseline machine code. And the idea here is like, just run this JavaScript code. That's all we want you to do. It does actually have an extra function, though. And the function here is we want to collect feedback on the types we see. So like Francie said earlier, when we're running JavaScript, we don't know the types of the things. It's not explicitly marked with types. And we can make optimizations once we know what those types are. So we run this code in the baseline phase, and we collect types. Then when we have enough types, and we've seen this function a lot, and it's becoming hot, we decide to optimize this function. And that's when we sent it to Crankshaft. So Crankshaft's the optimizing compiler. OK, so we take as our input the code that we want to run, and we take all this type information and all this other feedback, and we create super optimized code. And that's produced on the right there. And this is basically how we're running code in V8, or how we used to run code in V8. OK, so we changed it slightly. Now we have this new thing called Ignition and Turbofan, which we've been talking about. Ignition is an interpreter, not a compiler, so it's not producing machine code. It's just running the code. But it's the same sort of thing. We have this optimization phase. We have this feedback coming through. And we have a different optimizing compiler now. So what were the problems with Crankshaft? I mean, we totally deleted this thing, right? We didn't change it slightly. We just like changed it out for another one. So Crankshaft was starting to show its age. We couldn't directly support new language features, like ES6 features. So I mean, we supported them in V8, but we'd always support them in the slower runtime. It wasn't supported directly in optimized code. Crankshaft also had potential for a lot of de-optimization. So one arrow missing on that past slide is when we create optimized code, we make assumptions about the code, and we say, OK, we've seen this type a lot. We're going to optimize for that. If it turns out that assumption's false, we have to de-optimize and go back, right? And this sort of created huge performance cliffs. And when I say a performance cliff, what I mean is like your code runs super fast because you've always given it the same sort of string, not necessarily the same string, but the same sort of string, and it's so good. And then like you give it a string that's 1 character longer, and it's like, pfft, and it's like totally slow now, and you have no idea what's going on. I mean, it's an extreme example, but things like that, right? There are structural issues with Crankshaft as well. So there were no clear separation between the phases of compilation. We had to handwrite a lot of assembly code for 9 architectures, which is just not fun. It was, yeah, super buggy, and obviously lots of problems with it because of that. And full code gen also produced a lot of code, which is bad on mobile because it takes a lot of memory. OK, so some of the goals of Turbofan were provide dependable baseline performance. And this is an idea we're going to come to later in terms of what do we mean by performance. It's important to know that when we say, how do we write fast code? So part of the goals here are get wider fast paths that cover more of what you're trying to do, right, and reduce these performance cliffs. So we should have more predictable performance, not just higher peak performance, right? I think this pig is cute. OK, so there was a lot of performance advice floating around out there for Crankshaft. And OK, you can tell it's Crankshaft performance advice because it starts with the word don't. So a lot of it came down to things like, OK, we couldn't support a lot of language structures. So don't use let-const, don't use try-catch, don't use try-finally, don't use for-in, definitely don't use generators or async functions. And this is kind of a bad way, right, to have your language where it's like, yeah, we have all these cool features, don't use them. They're terrible. OK, so these are some of the sort of things we would see in CrankshaftScript TM. And you can actually look at the code that is CrankshaftScript. We're going to look at some, and you can see these sorts of things. But as I said, Crankshaft guessed way too much. It had terrible performance on bailout. It didn't support these these new language features, so we got rid of it. But also, it led to this situation where the communication with the community was sort of wrong, right? So we're sort of saying, OK, these things work fast in V8, so you should write your code like this in Node or for Chrome or whatever. You should write your code in a way that will run fast in V8. But this kind of created this dialect of CrankshaftScript, right? So now what we're trying to do is like, OK, actually make everything fast, listen to the community a bit more. OK, cool. So we're going to look at some code examples, just to give you an idea of what I mean by CrankshaftScript. OK, I don't mean to like code shame anybody. It's fine. This was really fast. OK, so I mean, that's kind of worth it. So the comment here says, this implementation of check is HTTP token loops over the string instead of using a regular expression, since the former is up to 180% faster with V8 4.9. OK, cool. That sounds good, right? So this is actually in Node core. And OK, so some of the problems with this. OK, V8 4.9, the current version is 6.2. So this is a while ago. So the question really is this code still fast in V8? I have no idea, right? So what is this code even trying to do? Well, it's trying to take a string, and it checks each character. It basically like filters each character and checks whether it's a valid character or a non-valid character, and then gives you a result for the whole string. It kind of does this by using this array, which is really, really long, and it has a 0 or a 1 for each character. And then you take the char code of the character, and you look it up in this array. And you can see they've peeled the top 3 iterations of the loop off manually as well, because it turns out this was faster. I have no idea why. Yeah, OK, this was way faster. Cool. But it's kind of hard to read what this does. I mean, you know it checks a HTTP token, because that's the name of the function. But you have to put this comment there, right? And if you're ever looking for CrankshaftScript, you can just grep for really long comments that have the word V8 in them. That's how I found all of these. OK, so this is actually what it used to look like. And the top is just a regex literal. And we take the thing, we check it's a string, and then we call regex.test on it. And you can actually see what the characters are. It's not in some giant like filter array thing. So part of the problem with the way it worked before with CrankshaftScript and everything like that is we create this brittle binding between the code and the engine, right? And it's really easily outdated. Like even by V8.5, that may not have been the case anymore. So you have to like either constantly measure this thing, constantly update it. It sort of really relies directly on the internals of V8, right? And what that tells us is that we aren't supporting real-world use cases, right? If people have to like crazily hack around things to do fairly simple algorithms like this, then maybe it should just be faster, right? It should be easy to do things that are fast, that are normal. If you're doing something like totally crazy, then maybe you need some hackery or something like that. But this is a fairly straightforward use case. So another example that I saw out there was, OK, so one of these pieces of advice was don't use try-catch because it's not optimizable in V8. And that was true. It's not true anymore, though. But so one way you could do this is if you have something that you want to optimize, say function bar, then you do that in one function, and then you have another function, foo, which wraps that. And you do the try-catch in the wrapping function, right? So you just like split this into 2 things. And then foo won't be optimized, but bar still can be optimized. So if this is like really hot code in your application, it could be worth doing this. And in V8 5.1, I just wrote a little micro benchmark here. That was 1.27x faster. OK, it's a little bit faster if we can optimize bar. And if bar is even bigger, then you probably get a better performance win. In V8 6.0, this makes literally no difference, whether you do it like this or whether you just like squish these 2 functions together, right? And that makes sense. That's the way it should be. OK, so it doesn't really make sense to do this anymore in V8 6 or later. But it's worth noting as well that this is actually 19 times faster overall from V8 5.1 to 6. So the real takeaway here is use the new version of V8, right? OK, another really long comment. These are great. This is in Ember, actually. This exists because object.createNull is absurdly slow compared to new empty object. In either case, you want a null prototype when you're treating the object instances as arbitrary dictionaries and don't want your keys colliding with the built-in methods on the default object prototype. So what they're saying is we want an empty object and we want it to have an empty prototype so we don't get collisions with the built-in methods. OK. So basically in Embo, there was this thing where instead of doing object.createNull, they had this special thing called an empty object, and they would initialize that instead. Maybe that actually semantically makes sense for your app. But also, it's a little bit hard to read, because as a developer, you come in and you look at it, and you're like, oh, what is empty object? Then you have to look it up, right? So basically, the only difference here is you would call new empty object, or you would just go object.createNull, where null is the prototype of the object you want to create. So in V8 5.1, in a really silly benchmark I made, this was actually 10 times faster to do it this way with new empty object compared to V8 6.0. Sorry, in Crankshaft compared to Turbofan. In V8 6.0, this makes absolutely no difference. Cool, OK. And it's 5 times faster overall again. So again, just use the new version of V8, please. Someone had a real dog earlier, so I wanted to sort of bring that in here for the cuteness break, but I think it's gone. OK, so back to that main question of how do I make my JavaScript really fast in V8. So I told you that CrankshaftScript is gone, and please don't use that. So now you're like, OK, tell me what Turbofan script looks like, right? Yeah, I'm not going to do that. So, I mean, hopefully, the real goal here is that fast JavaScript for Turbofan and for V8 and for the web in general should look like regular readable JavaScript, right? That's not a totally wild idea. This is pretty straightforward. It would be really nice if you could just write the most readable code you want, self-documenting, idiomatic JS, and it was really fast as well. And that's what we want to do. And I think that's what everyone wants. You should be able to use all the new features, ES6 features and stuff like that. And it should work well on any engine. So if you're running Node, then OK, it's going to be running in V8. But maybe you want to run Chakra Node. OK. Or if you're writing something for a web browser, then you have no choice which engine it's going to run on, right? So Ignition and Turbofan are stable in Chrome at the moment. So if you're using Chrome, then you're already using them. And it's also released in Node and will be in the next LTS. So that's good, too. OK, so how do we get to this state? Well, I'm going to blame micro benchmarks. So micro benchmarks are really great at measuring one thing. It's really hard to know what that one thing is. So it's really easy to write a micro benchmark. It takes maybe 1 minute or something. And it takes like 2 to 3 days to actually figure out what you're measuring with that thing. They rarely stress optimizing compilers in the right way. This is what I figured out. So I want to look at an example of when I was working on performance for typed arrays. So typed arrays back the buffer class in Node.js. So fairly fundamental. So Crankshaft loves this type of thing, right? So if you want to create a new uint32 array, you can create it from an existing array. And say you create it from an existing typed array, which is a uint8 array. You do this over and over again in a tight loop. This was the type of benchmark we had for typed arrays. And basically, we looked at a bunch of benchmarks, and we saw, OK, these are going to regress when we release Turbofan. So before Turbofan's release, we're going to work on these. So this works really well in Crankshaft because the new type you're creating, so you're always creating a uint32 array, and the target, the uint8 array, are always the same type each time, right? And when we ran this in Crankshaft a lot, OK, it was much faster than it was in Turbofan. Then we worked on Turbofan, and now they're the same speed. OK, great. But we didn't really win anything because we just made Turbofan as fast as Crankshaft was, right? So why do we bother doing that? Well, what we're measuring here is peak performance. So we're just doing the same thing over and over again. There's not many crazy types going on. It's fairly predictable, which is what Crankshaft was kind of good at. But what happens if we add another thing into our micro benchmark here, and we create from an int8 array as well? OK, and then what happens if we add the 16-byte ones as well, and the 32, and the floats, and the clamped? OK, now we actually have a lot more going on in our micro benchmark. Maybe it's not so micro anymore. And then you think, OK, we're only changing the target here. What if we change the type we're creating as well, right? And we actually have this whole matrix of different types that this thing could run into. And it sort of explodes from there. And yeah, so this benchmark runs equally well in Crankshaft and Turbofan, this simple one. But this benchmark runs 5 times faster in Turbofan, right? So Turbofan is much better at handling these sorts of cases. And that's really what we were looking to do with that. So benchmarks basically don't tell you the whole story sometimes. Peak performance gains are impressive. And it's great to write a micro benchmark and be like, this feature is this fast. Yes, love it. But it sort of gives rise to this idea that you can just write this one little piece of code and test it, and it runs this fast, and that's great, and that's all we're going to do. We're not going to look at it anymore. But we need to also think about the predictability of the performance, because the problem with that Crankshaft example is if you suddenly add one other call to the constructor of a typed array in there somewhere, or someone else in your app does, or your framework does that, then it's like, pfft, and goes way slower, right? So this is these performance cliffs we were talking about earlier. So this is where the real-world benchmarks come in. And when we look at Turbofan, OK, on most of the micro benchmarks, it's like basically the same as Crankshaft. But when you look at real-world benchmarks, it's way faster. So the takeaways, what I want you to take away from this talk is, please stop writing CrankshaftScript. It doesn't work anymore anyway. So OK, aim for the average case, not the peak performance case. So think about whether your benchmark is hitting peak performance and whether that's really the ideal case, or whether once you get all this like production data hitting your server, you're actually going to have different types and things like that. And we want your use cases as well. So if you're running a Node app and you're like, oh, I think it's running a bit slower, or it's not going as well in Turbofan, or something like that, or you think you've got an interesting performance case, we want to hear about it. So thanks very much. You can reach me at petermarshall@google.com. You can log a bug on the V8 tracker. It doesn't need to be really specific. You can just be like, here's my app. It's slow. No, don't do that. But bit more specific. OK. I don't have Twitter, but you can just reach other people on Twitter, and they'll contact me. So Benedict Mora, Matthias, or Francis Engelman. Check out Young's talk tomorrow, Thursday, 11:20 a.m., new DevTools features for JavaScript. I'm happy to take any questions. Thank you. Don't be scared of asking questions. I'm scared of answering them. What is it bad at? What is Turbofan bad at? What do you think, Young? Nothing. Yeah, it's great. The talk is done. Yeah, man. Yeah. Yeah, so yeah, we're still doing a lot of work to support newer language features directly in optimized code. Yeah, and there's still some edge cases out there as well, which is sort of what we're looking into. So if you have any examples of that, then we'd love to see it. Yeah, down there. Yeah, I mean, the basic concept is that Crankshaft guessed too much, so it performs speculative optimization by saying, OK, I've seen these sorts of things. I'm going to take that and run with it and make some super optimized code for that case, right? And Turbofan does the same thing, but the way Crankshaft did it was really aggressive, basically, in a lot of ways. And then it would, you would get these de-optimizations. And so when you have optimized code and some assumption fails, we go back to this de-optimized. We de-optimize and go back to the baseline code, right? And if we do that enough times, then we'll never try and optimize that code again. So yeah, that kind of answers your question, I think. We can talk about it afterwards, too. Yeah, just here. Yeah, so OK, yeah, so there are lots of different dialects of JavaScript. The question is, do we study them or like look at them? So I guess also, as well as full-blown dialects, there are things like common idioms and patterns, right? So one way we look at this is when we implement a new feature, so there's a new feature in the spec, or we want to stage a feature if it's at stage 3 or something like that, we just implement this feature most of the time, just like we just implement it baseline in the runtime, and we just get it working, and we get it spec compliant, and we write all the tests. But we don't care too much about performance initially. I mean, we do, but one of the things we want to do is gather feedback about how people are using this feature and what the common idioms and patterns with this feature are. Because we don't know what the fast paths need to be, or we don't know how people are going to use this, or in combination with what other features. So that's part of where those idioms come into it and how we're looking at it. Anything else? Thank you.